before going to luminous intensity and candela, you must have a basic idea about what is solid angle. Angle is defined at length of arc by radius. That is the definition of normal angle subtended by an arc, circular arc at the center of a circle. So this is the angle, this is represented in radians. This is represented in radians. The value of angle is given by length of this arc. Let this length is AB. Length of this arc divided by radius. So theta is AB by R. For complete circle, we know circumference is 2 pi r and radius is r. So complete circle subtends an angle at center is which is 2 pi radians. Angle subtended by a complete circle at center is 2 pi radian based on the definition of plane angle. Similarly, solid angle, it is, you have to replace this arc from a surface area. So solid angle, let this is a sphere. This is a sphere. So solid angle subtended at the center of a sphere is given by area of an element on the periphery of circumference or periphery of this sphere divided by r square. So whenever you are finding solid angle by an area, so just complete a sphere analogous to normal plane angle. Suppose these are two lines of different length. You want to know angle at this point. You just make a circle of radius r. Measure the length of this arc AB. So angle theta is AB by r. Same analogy in case of sphere. If you have a area, this is the area. How much solid angle it will subtend at this point? So this area is subtending a solid angle at center, similar to this plane angle. So just make a sphere crossing this region. Make a sphere which crosses this region, which is shade of this area under consideration. So the solid angle subtended by this area will be same as solid angle subtended by this irregular area. Just similar to this, solid angle subtended by this arc AB is similar to angle subtended by this length at center. So let this is CD. So the angle subtended by CD and angle subtended by arc AB at O are same. So angle subtended by CD we can find by drawing a circle which passes through these lines, which are lines coming from CD to O, and we will form a arc AB. By this formula, arc divided by radius, we can find angle in radian. Similarly here, this is an area, and this area is subtending a solid angle. When we will take all lines from periphery of this area and join these all lines at the center, so it will make a volume. Here it is making a area, this will make a volume when all lines coming from edges of this area are joined with this O center, then it will construct a volume. So just make a sphere, arbitrary sphere crossing this volumetric area, and now you can find solid angle subtended by this area at center, which will be same as solid angle subtended by intercepted part of sphere. That this is A, B, C, D. That is area of sphere. So the solid angle at center is this area. Let this area is A. So this area is A dash. This area may be different. Similar to this, the length of arc is not necessarily equal to CD. Similarly, area of this intercepted part may not be equal to this area. But the angle subtended by both area at center is same, solid angle. So solid angle is given by this area, that is A dash, this area, divided by R square. That is the method to find solid angle, similar to this analogy. Similarly, for a complete sphere, we know complete sphere area is 4 pi R square divided by R square. We cancel and this is 4 pi. So a complete sphere subtends an angle of 4 pi steradian at the center of the sphere. So candela is the unit to measure the luminous intensity. So what is luminous intensity and how it is felt, how we feel the luminous intensity? So we know that, for example, if there is a bulb, let this is a bulb. This bulb consumes 10 kilowatt. This bulb consumes 10 kilowatt electricity. So this 10 kilowatt electricity will be converted into light plus heat. So this 10 kilowatt electricity will be converted into light. Light means it will emit radiation. This bulb is emitting radiation. In this radiation, some radiation is falling in visible range and some radiation is not falling in visible range. The radiation which is falling in visible range can be seen by our eyes. That is called light. It will have some colors, green, yellow, red, some colors. It may have other colors. These colors are visible. Those all colors comes under light. Red, green, blue, yellow, all colors will come under light. And rest energy. Let the energy associated with light is 6 watt. Energy associated with red, green, blue, yellow, all lights emitted by this bulb is 6 watt. So rest 4 watt energy, electricity, is heat. Heat means that is also electromagnetic radiation, but it is not visible to our eyes. It is some other range. There are other ranges of electromagnetic radiation except visible range. So 4 watt is heat, it is not visible, and 6 watt is light, that is visible to our eyes. So what is luminous intensity? Luminous intensity measures the brightness. Brightness means which can be seen by our eyes. So we will not say that the luminous intensity of this bulb is 10 kilowatt. It is only converting 6 watt. sorry, this kilowatt, then you can use kilowatt here also. 4 kilowatt. It is 10 kilowatt, 6 kilowatt light energy and 4 kilowatt as heat energy. I have used kilowatt, very big unit. Generally bulbs are in watt. You might have seen that CFLs are 9 watt, 10 watt, 20 watt. So these are the in wattage. For example, if you have taken kilowatt, then doesn't matter. So out of 10 kilowatt, 6 kilowatt is converted into light and 4 kilowatt is converted into heat. So luminous intensity considers only light part of the radiation. So first component which is considered in luminous intensity is visible radiation. Visible radiation. Second part is our eye, sensitivity of our eye. Sensitivity of our eye is not equal for all types of visible radiation. That means sensitivity is not same for green, yellow, red, etc. So this component which deals with the sensitivity of our eye for different type of color is considered by luminosity function. Luminosity function gives weightage, different weightage to different colors based on the sensitivity of our eye for different type of colors. So second factor is sensitivity of eye. So these two factors contributes for luminous intensity. So our eye is sensitive for particular type of radiation which is falls under somewhat under green range. For light is if some source is emitting in that range, even it is possible for sensitive radiation for lower power radiation for which our eye is more sensitive may appear brighter than other radiation which is of higher power, but our eye is less sensitive for that radiation. Candela is a base unit in SI system, International System of Units, which represents luminous intensity of a source. So in early days, near 1860, the name of this unit, candela, came from candle, simple candle, wax candle. So in early days, candela was one candela was assumed to be the intensity given by a wax candle. A wax candle source is burning and the intensity felt by illumination intensity felt by our eye for that candle was standardized as one candle. So after that in 1860 this candle was also fixed and this candle was made from fat of whale fish. Burning of that candle was assumed to be producing one candela luminous intensity in 1860. After that, other standard sources were discovered in 1898. Different sources, some burners which were using pentane gas, they were used to standardize this luminous intensity. In 1948, one candela was officially defined by CIPM, International Committee for Weight and Measures, which works under CGPM, General Conference for Weight and Measures. So the new definition of candela was given based on platinum metal, or we can say black body radiation, black body radiation. So a black body is considered as a perfect absorber or perfect emitter, which is an ideal body. We all know black body is an ideal body and no practical surface can behave like a black body. So this black body radiation was used to define, to standardize the candela. To achieve the black body radiation, the melting point of platinum metal was used as a reference temperature. Melting point of the platinum metal was used as a reference temperature. At that temperature, the luminous intensity of a black body radiation surface, black body radiating surface, was assumed as 1 candela. Again repeating, a black body radiation at the temperature equal to melting point of platinum metal was assumed to be 1 candela in 1948. As this definition was based on the black body radiation, so this was called new candela. After that, this new candela was again redefined in 1967. In 1967, CGPM, General Conference for Weight and Measures, redefined 1 candela. That was also based on black body radiation, but it also included atmospheric pressure. It defined 1 candela as luminous intensity, 1 candela as luminous intensity from 1 by 6 lakh meter square, this much area of black body at melting point of platinum at 1 atmospheric pressure. So in 1967, 1 candela was defined as black body radiation from 1 by 6 lakh meter square area at melting point of platinum at 1 atmospheric pressure. So the latest definition of candela was changed in 1979 during 16th CGPM meeting. CGPM is General Conference for Weight and Measures. 16th CGPM meeting, a resolution was passed to redefine the candela in 1979. In 1979, candela was defined based on a known source of monochromatic light. Known source of monochromatic light for which our eye is most sensitive. For the new definition in 1979 during 16th CGPM meeting, resolution was passed to redefine the candela. So 1 candela for a source in a particular direction was defined as a luminous intensity for 540 into 10 power 12 hertz radiation, monochromatic radiation in unit solid angle having power equal to 1 by 683 watt. When the power of the source which is emitting light, which is emitting monochromatic light, is 1 by 683. This is the power of the source, 1 by 683 watt per steradian. So 1 candela is nothing but luminous intensity for most sensitive monochromatic radiation of our eyes for a source having this watt power in unit solid angle. So here another important thing is that as this is a monochromatic source, only emitting 1 wavelength light, so whole this energy wattage will be converted into visible light of this frequency radiation. As we have discussed, candela is a measure of brightness of a source which is emitting the light, visible light, that is measured by candela. And candela is defined for a particular direction in a source. Visible light, and it is defined only for visible light. Now lumen is also defined for a source. It also measures brightness of the source. But the difference between candela and lumen is lumen defines total visible light emitted by source in all directions. So candela is for a particular direction, particular angle. So this is a source. So in this direction, luminous intensity is something else. In this direction, it can be something else. So that is defined by candela. Lumen is total intensity. So lumen is it is also unit. It is called luminous flux. It is a unit of luminous flux, and it is achieved by luminous intensity, that is candela, into solid angle. You can interpret it like this. Lumen is for a given source of light. It is in a luminous flux for a given solid angle region. So candela and lumen both are used to find the brightness of source. Candela is defined for a source in a particular direction in unit solid angle region, whereas lumen is defined for all directions, total brightness in all directions. That is candela into this solid angle. Candela into solid angle to get a lumen in that region. Candela into 4 pi, then you will get total lumen in total spherical region. So the third unit which we are using in illuminance is lux. So lux is unit of illuminance for a surface on which light is falling. So suppose 50 lumen flux are falling on a area A, surface having area A. Then on unit surface area, you can say 50 by A, lumen flux is falling. So this 50 by A lumen per meter square is called illuminance, and this illuminance is represented by lux. So lux is nothing but luminous flux in unit area. Luminous flux in unit area or lumen per meter square, and candela is lumen per steradian. So in short you can say candela is lumen per steradian and lux is lumen per meter square. So luminous flux per meter square, that is lumen per meter square, is called lux, and lumen per steradian, that is flux in unit solid angle, is called candela.